Welcome to NE204 Lab 9. In this lab, we'll build and train a perceptron. We'll start in the first part of this lab by constructing a simple perceptron similar to what you saw in lecture, and then we'll continue to outline the steps to train a perceptron to classify a point as either above or below a line. You'll find that this lab, as well as the lectures you had earlier this week, are a little bit more complicated, more technical than what you've seen earlier in this course. But I'm confident you're prepared. So let's dive into this and start implementing our perceptron models. In part 1 of this lab, we'll construct a simple perceptron model. In class, we discussed the perceptron, how it accepts a series of inputs, processes those inputs in a particular way, and then returns an output. So let's start by examining a function that performs this perceptron computation. To do so, please go to Blackboard and download the function myperceptron.m. You'll find that function in the lab for this week. So do that first. Then after you do so, come back and continue this video. So after you've downloaded this function, let's have a look at it. So I'll look at this function myperceptron.m and see if we can make sense of this function. Well, what we see is that this function receives 5 inputs. These inputs correspond to input 1 and 2 to our perceptron. We can think of these as 2 inputs to our perceptron. Each of those is weighted by a particular weight, W1 and W2. And then we have a bias term that we defined as theta. Now this perceptron is consistent with the figure that we drew in our examples in class. So let's look at that figure here. Notice that the perceptron takes 2 inputs that we've labeled input 1 and 2. These are weighted by weights W1 and W2. There's a bias term, theta. And what we'd like to do is know the output of this perceptron. In this case, we're going to assume a binary threshold, just as we did in class. So let's see if we can look at this code and understand the computations that are performed and whether or not they're consistent with our expectations. So the first thing we'll do is compute the activity of our perceptron, our neuron. Let's call that activity x. And to find x, we're going to take input 1, multiply it by its weight, add to that input 2 multiplied by its weight, and then add to that our bias term theta, just as we had done in lecture. Now, we're ready to compute the output of our perceptron, and we'll do that using a binary threshold. So if x is big enough, so if it's greater than 0, we'll set the output of our perceptron to 1. Otherwise, we'll set the output of the perceptron to 0. Notice we're using an if-else statement in this case. If one thing happens, do this. Otherwise, do this. In this if-else statement, we always end it with an end. So that's the function. The function returns the output. It's binary, either 1 or 0, and we specify these 5 inputs. Again, consistent with the figure that we drew in class. Our perceptron receives 2 inputs that we label input 1 and input 2. We have 2 weights, W1 and W2, and then we have our bias term, theta. So if we go back to the lab for this week, we've answered some of these questions. How many inputs does our function take? We saw that it takes 5. How many outputs does it return? In this case, it returns 1 output, a 0 or 1, a binary output. And then looking at this code, here's another question. Because you sketch a model of this perceptron, similar to what the models we drew in lecture. Well, we've already kind of done that. I've told you that the code that we're using in this case matches exactly the model that we drew in class. Here we have our perceptron. It has 2 inputs, each has a weight, and then 1 output. Also a bias term. Okay, so let's now apply this function and see how it behaves. To do that, we're going to consider different types of inputs. So let's consider this first case where we set our input 1 to 1, input 2 to 0. We specify our weights to be 0.5 for input 1 and minus 0.5 for input 2, and we set our bias term to 0. So in this case, we can think of the bias term as being off. So to implement this, first I'm going to define all of these terms. So I'll set input 1 to 1, input 2, I'm plugging this into the command line to 0. I'll use a semicolon here, I don't need to print it out. Let's set weight 1 to 0.5, weight 2 to minus 0.5, and then our bias term theta, we'll set that to 0. Okay, so I've just entered these 5 scalars, these 5 variables, into our MATLAB. We can see it in the workspace. And now let's call our function. If I go back and look at the function, I'm just going to copy the first line of this function. That'll make it easier to compute. And then I'm going to paste that into the MATLAB command line. So notice what I've done here. So we're going to call the function myperceptron. It's going to take input 1 and input 2. We've defined those 2 terms. We've said input 1 is 1. I can see it in my workspace. And input 2 is 0. We also need to specify W1 and W2, our weights, which we've done up here. W1 is 0.5 minus, W2 is minus 0.5. And then our bias term theta is 0. Now in this particular case, we've happened to set these inputs, right, these variable names, to match what our function specification. That doesn't always have to be the case. For example, this last term, we could just specify a number, right? Instead of typing theta, we could put a 0 there. But I'm going to use theta since we've already defined it. Or maybe we called our bias term, maybe we labeled it something else. Instead of theta, we could label it bias. And then we'd have to replace this theta input with bias. So the important thing here is all of these variables that we're sending to our function are defined in our workspace. Right? We could check that. Input 1, input 2, yes, defined in our workspace. W1, W2, also defined in our workspace. Theta, defined in our workspace. Okay, so let's do this. Let's call this function now and see what happens. So I'll execute this command. It doesn't crash, that's good. If yours does crash, make sure you can access the file myperceptron. Make sure it's in your working directory. If that's not the case, then it might crash. Say, I can't find this function. So make sure MATLAB knows where this function is. Okay, and now let's look at the output. We find that the output in this case is 1. That's consistent with what you found in lecture. So this is one of the examples we computed in lecture. The output is 1, and we find that our computation here in MATLAB matches that result. Let's consider another example. What if we changed the bias term? So in the second example, we're going to keep input 1 the same, input 2 the same, the weights the same, and we're just going to change the bias term. So to do that, I'll change theta, and instead of setting it to 0 as we did in the first example, let's set it to -1. So we'll do that here. We'll call the function again. I'll hit up arrow a couple of times until I get back to this function call. We're going to compute the output of my perceptron. We're going to use the same inputs, input 1 and input 2, the same weights, W1 and W2. And now we've changed theta. Notice that theta is now -1. We can see that here we've just executed this command where we've set theta equal to -1. And we can also see it in our workspace at the top of the screen. Theta is equal to -1. So if I execute this command, good, it doesn't crash. Let's see, what is output? What do we get in this case? In this case, it's 0. So by making the bias more negative, we've changed the output from our neuron. When our bias was 0, we had an output of 1. With a bias of -1, we have an output of 0. And again, if you compare these results to those you found in lecture, they're the same. So you might go back and look at those examples and compare them to the MATLAB code we've computed here. Part 1 of this lab was a warm-up exercise, computing a perceptron's output given 2 inputs. The second part of this lab is the meat of it, the more challenging part. And what we're going to do in the second part of this lab is to build our perceptron classifier. We discussed a method to do this in class with a particular application. We'd like our perceptron to tell us whether or not a point is above or below a line. And in lecture, we discussed 5 steps of training a perceptron in order to achieve this classification. Is the point above or below a line? Let's look at these 5 steps here. The first step is to provide the perceptron with an input. So we're going to choose an XY point and the known answer. We then ask the perceptron to guess an answer, that's step 2, and we compute the error. We ask, does the perceptron get the right answer or the wrong answer? To do this, we need to do step 1. We have to know the right answer, and then we're going to use this to train our perceptron. We ask, what does it get, and compare our known answer to the perceptron's answer. In step 4, we adjust all the weights according to the error. This is the learning step. And then we repeat steps 1 through 4 over and over and over again. So our goal in this part of the lab is to implement each one of these steps. Let's begin with step 1, where we'll provide an input that we'll use for our perceptron and also a known answer. Now in order to compute the known answer, we're going to make a new function. And this function is going to compute a line where we specify the intercept and slope, and then we're going to give it our input point, x and y, and ask, is the value y that we specify in our plane above or below the line? It's important to have this function that gives us the correct or known answer because we need these known answers, the correct answers, to train our perceptron. When it gets it wrong, we want to change our perceptron's weights, and if it gets it right, we just don't do anything. So again, we'll use these known answers that we'll develop in this function to tell when our perceptron is right or wrong, and that'll occur in later steps as we go along. Okay, so let's define this new function. We'll call it knownanswer.m. And this new function is going to take 4 inputs. We need to define our line. So to our known answer function, we're going to give a slope and an intercept. So we get to choose what those are. And we're also going to give it the point in the plane. So those will be inputs 3 and 4, x and y. And what we'd like to do is, given this value of x and y, that's this point in the plane, we want our function to return one output, the desired output, where this desired output is 1 if the y that we specify, this y value, the last input in the line above, is above or below the line. And actually, I see a typo here now. It'd be clear if this was instead y. So we'll make this y here. So what is this desired output? The desired output is 1 if y, the last input, is above the line. It's the last input to our function. And the desired output is 0 if y, the last input, is below the line. When we specify these by convention, it's maybe more intuitive. Above the line, let's make that 1. Below the line, 0. And again, this is the desired output. This is the thing that we know. So in order to compute this known answer, please go to Blackboard and download this function knownanswer.m. And what we'll do is examine this function. So now that you've downloaded this function knownanswer.m, let's have a look at it. So here's the function knownanswer. We said it takes 4 inputs, the slope and intercept of our line, and then the x and y coordinates of the point in the plane. It's going to return one output, the desired output. Is the point y, the last input here, above or below the line? Okay, so how does this function work? What we're going to do is first compute the y value on the line. In order to do that, we're going to take our x value of our point, multiply by the slope, and then add the intercept. And that'll give us the y value on the line corresponding to the x value of our input. We're then going to ask a question. Is the y value of our point in the plane, the variable y, greater than the y value on the line? And if that's the case, then y, our point in the input, is above the line and the desired output is 1. Otherwise, y is below the line, our y point is below the line, and the desired output is 0. So that's how this function knownanswer behaves. We give it the 4 inputs, the slope and intercept of our line, the xy coordinates of our point, and it returns the desired output. This is the correct answer. Either 1 if y is above the line or 0 if it's below the line. So let's go back to the lab. We can think about some of these questions. Hopefully this function now makes sense. And hopefully we're able to see how the function compares the input y value of our xy point and determines whether this y is above or below the line. So now let's see how this function behaves. In order to do that, we're going to specify a point in the xy plane. And let's choose a particular point. Let's set x equals 0.7 and y equals 3. So I'll paste that into the MATLAB command line. This is identical to the example we worked out in class. And we're also going to specify a line with a slope and intercept. So here's the slope and intercept that we're going to use. We'll set the slope equal to 2 and the intercept equal to 1. Again, exactly matching what you saw in lecture. And what we'd like to know is this point that we've specified, is this xy point above or below the line? Well, in order to answer that question, we could try to work it out by hand, or we could call our new function. So let's call this function knownanswer. It takes 4 inputs. We have to specify the slope, which we've already defined, the intercept, which we've already defined to be 1, and the x and y coordinates, where we set x and y equal to 0.7 and 3. So we can input all of these variables, slope, intercept, xy, because we've already defined them, give them numerical values in the command line. If we execute this command, it returns the desired output. Right, and maybe I'll define that here. Let's set the desired output equal to our function call, the known answer. So if we evaluate this expression, we find the desired output is 1. So what does this mean? Well, we can look back at our key. If the desired output is 1, that tells us that the y value that we specified is above the line. If you want, you go back in your notes and check that. This point xy is above the line with slope 2 and intercept 1. This completes the first step of our Perceptron training procedure. We now have an xy point that we've specified, and we have a known answer. This point is above the line. On to step 2, where our goal here is to ask our perceptron to guess an answer. Now in the first step, we computed the desired output. This is the known answer. And what we'd like to do is compare this desired output to the output produced or guessed by the perceptron. In order to do that, we need to compute the feed-forward solution for the perceptron, which means that given the inputs and the bias to our perceptron, let's compute the output, our feed-forward solution. To do that, we're going to download a function, another function from Blackboard. Please download this function, feedforward.m. You'll find it in Lab 9 from Week 9. And what we'll see after you've downloaded this function is that it takes 5 inputs. We'll look at the function in a minute. First, let's look at the inputs. We're going to specify the x and y coordinate of the point in the plane that we're interested in. We're going to specify the weights of our perceptron, the weight for the x input, wx, and the weight for the y input, wy, and also the weight for our bias term, wb. Those are the 5 inputs. And this function, this feed-forward function, then returns one output. And that output is the perceptron's guess. It's going to guess, is the point above the line, in which case it returns a value of 1, or is the point below the line, in which case it returns a value 0. Again, we have this binary output, our perceptron's guess. So let's have a look at this function and see if it makes sense. We see that our feed-forward function takes 5 inputs, the x and y coordinates of our point in the plane, the weights wx, wy of the inputs, and also the weight for the bias term, wb. We see it returns one output. We'll get to that output towards the end. In our perceptron model, we're always going to fix the bias equal to 1, so we set that here. And then we're going to define the activity of the neuron, which here we're going to call activity. So what is that activity? Well, we're going to take the x coordinate, multiply it by its weight, add to that the y coordinate multiplied by its weight, wy, and then add to that the bias term multiplied by its weight. We're going to sum up all of those terms, and we'll call that the activity. And then we'll apply the binary threshold to this activity. If the activity is big enough, if it's greater than 0, we set the output of our perceptron to 1. Otherwise, we set it to 0. So again, this is our feed-forward calculation. Given our point x, y, and the weights, the 3 weights, wx, wy, and wb, we're going to compute an output. So hopefully you can look at this function. You can see the calculation of the activity, and this should make sense. And also you can see the binary threshold, where again, we're using this if-else statement. If the activity is big enough, the output is 1. Otherwise, else, it's 0. Let's return now to the lab and apply this function and see how it behaves. So what we'll do in this case is we're going to again consider the point that we defined earlier. So let's consider the point x equals 0.7, y equals 3. I see in my workspace x is already equal to 0.7, y equals 3. I'll type it in here again just to be sure. So we have x equals 0.7, y is 3. And now to calculate our feed-forward solution to our perceptron, we need to set the weights. And we're going to initially set all of the weights to 0.5. These initial weights are arbitrary. We don't know what the weights should be. That's why we're training the perception. We want to find the right weights. But for now, let's just set all of the weights equal to 0.5. So wx equals 0.5, wy equals 0.5, and wb equals 0.5. Then we're going to ask the perceptron to guess an output. To do that, we'll compute the feed-forward solution. We'll give it the x and y coordinates of our point, and we'll also specify the weights wx, wy, and wb. And let's compute the perceptron output. So I execute this command, no errors. That's good news. If you do get an error, you might make sure that all of your inputs to the function are defined. Make sure all of these values have a number associated with them, and you can see it in the workspace. And also make sure this function feedforward.m, you've downloaded it and put it into your working directory. So let's see, what is the perceptron output in this case? In this case, it's 1. Our perceptron is telling us its guess in this case is that the point xy, where x is 0.7 and y is 3, is above the line. In the next step in this lab, we'll compare this guess to our desired output. On to step 3, compute the error. In the previous 2 steps, we've answered the question, is the xy point above the line in 2 ways? First, we computed the known answer. We did that in step 1. And second, we computed the perceptron's guess. What we'd now like to do is compute the error as the difference between these 2 answers. I have good news. This step is relatively straightforward. So what we're going to do is define a new variable, error, and we're going to set that error equal to the desired output. That's the output we know, the correct answer that we specified in step 1. And we're going to subtract from that the perceptron's output. Now let's do that in this case. For the particular point that we've been investigating so far, we've been looking at the point x is equal to 0.7, y is equal to 3. And we want to know, is that above or below our line, where we specified a line to have slope 2 and to have intercept 1. We computed these two variables, desired output in step 1, perceptron output in step 2. Let's compute this error. So I'll compute the error here. I'll paste that into the MATLAB command line and hit enter. And what do we find in this case? We find that the error is 0. In this case, our desired output is 1. The point is above the line. The perceptron's guess is also 1. It says the point is above the line. And this should make sense for this first example. It's identical to what you saw in class. This point is above the line, and luckily our perceptron gets the right answer in this case. So the error is 0. Now, step 4. We'd like to adjust all of the weights according to the error. Remember the expression that we found or proposed in class. Here I've written it in MATLAB code. I'll also paste it here matching our lecture notes. So what we'd like to do is define the new weight. And that new weight is going to equal the current weight plus the error in our perceptron's output versus the desired output, the input to that particular weight, that could be the x or y coordinate or the bias term, and then this other term, a learning constant, some number we specify. We won't get into the details of this learning constant here. Suffice it to say, we'll keep the learning constant small so that our changes in weight are relatively small. Notice if the learning constant is a tiny number, we're going to adjust our current weight by error times input times learning constant. This entire term, error times input times learning constant, will be tiny if the learning constant is tiny. Okay, so we need to compute this new weight for each weight in our perceptron. We have the weight for the x coordinate, the y coordinate, and the bias. So let's set the learning constant to be a tiny number. Here, let's set it to be 0.01. Then we can compute the new weights. And let's see how we do this. Well, what we're going to do is take our existing weight, Wx. We're going to add to it the error term times the x input times the learning constant. And this will give us our new weight, which we're also going to call Wx. And this line of code can be somewhat confusing. We have Wx on the left-hand side of our equation and on the right-hand side of our equation. So what's happening here? Well, by setting the Wx equal to Wx plus other stuff, we're going to write over the variable Wx. Initially, Wx has some value. We're going to add to it this stuff. So we're going to add to it error times x times learning constant, and then take that new summed quantity and set that equal to Wx. So hopefully that notation makes some sense. We're going to take the old weight, the existing weight, we're going to add stuff to it, and then we're going to call Wx the new weight. We're going to do the same thing for Wy. We're going to take its current value, we're going to add to it the error times the y coordinate times the learning constant, and we're going to set that equal to Wy. And then we'll do the same for the bias. We're going to take our bias weight, we're going to add to it the error times the bias, which in our case is always 1, times the learning constant. So let's evaluate this snippet of code and see what happens to our weights. So the first thing I'll do is define the learning constant. So let's define that here. And before continuing, let's look at the weights that we have currently defined. So we've set Wb equal to 0.5, Wx equal to 0.5, and Wy equal to 0.5. We're now going to compute the new weights. So we're going to redefine Wx, and we're going to set Wx equal to itself plus error times x times learning constant. What is Wx? Well, it's still 0.5. Why hasn't it changed? I thought we were supposed to be updating the weights. Why is Wx still 0.5? That was the initial value we chose. So what's happening here is, remember, our error is 0. For this particular point, our perceptron's guess was the same as the desired output. Both the perceptron and our known result say that this point is above the line. So because this error term is 0, what happens? We have Wx is equal to Wx plus 0. So there's no change in Wx. There's no update. The same is true for these other calculations. Wy is equal to Wy plus error times y times learning constant. So we'll evaluate that. We see Wy doesn't change, of course, because the error is 0. What about Wb? Okay, got an error here. So what's happened? WB is equal to WB plus error times bias times learning constant. Undefined function or variable bias. Why is that the case? Well, we haven't defined bias in the workspace. I'm going to go up here and look for it. I don't see bias in here. So we've not defined bias in the workspace. Where did we define bias? Well, it's hidden inside one of our functions. And that variable, which is hidden inside a function, is not accessible to us in the workspace. So the thing we need to remember here is that our bias is always 1. So we should set WB is equal to WB plus error times 1 times the learning constant. And that's the correct thing. That's what we want to do. The bias is always 1. We'll evaluate this. What happens to WB? Well, it doesn't matter in this case because our error is 0. So now what we've done, we've updated all of the weights. In this case, the update actually didn't change the weights because our desired output and our perceptrons output were the same. We're almost there. The last step, step 5. Now, unfortunately, what step 5 tells us is we have to go back to steps 1 through 4 and repeat them. It's actually a pretty complicated step. And you might imagine that we could try to compute these repetitions by hand. For example, by executing the cells above. And to do this, we'd have to choose a new point in the xy plane, determine whether it's above the line. In our case, the particular line we're interested in is 2x plus 1. So this is the desired output. Then ask the perceptron to guess whether this point is above the line, and use the error between our desired output, the correct answer, and the perceptron's output. Use the error between those two to update the perceptron's weights. And maybe you could do this by evaluating the cells above over and over and over again to repeat steps 1 through 4. But what if we want to evaluate this procedure 2,000 times? You could try to do this by hand, but it would be a total pain to do it 2,000 times, and also, at least for me, highly error prone. The probability of me making a mistake, typing in something wrong, if I were to repeat this 2,000 times is 100%. I would almost certainly make an error. So instead, what we're going to do is ask the computer to do the hard work of these boring computations. And maybe I shouldn't call it hard work. This is the boring work. We've done the hard work of thinking how to implement this procedure in MATLAB. And then we're going to ask the computer to repeat this procedure over and over and over again, just grinding through. Not interesting for us, very simple for a computer to do. So in order to execute step 5 and repeat steps 1 through 4 over and over and over again, we're going to collect the code above and examine 2,000 xy points that we place randomly in the xy plane. And what we're going to do is wrap our code inside of a for loop to try to make this more efficient. And let's see how this works. The first thing we're going to do is clear our workspace. We're going to start everything over to make sure we're implementing it correctly. So I clear the workspace. If I look in the workspace, I see there are no variables left. We'll then define the slope and intercept for our line. We'll use the same slope and intercept, slope of 2 and an intercept of 1. And we'll choose initial weights for our perceptron. We're going to start the weights of the x input, y input, and bias all equal to 0.5. You could choose other values. I'm going to set them equal to 0.5 here. We'll also set the learning constant equal to 0.01. Again, we choose this to be a small value. If you're interested in the details, I could point you to some references, or you could take more classes on how to develop these types of learning procedures. But for now, suffice it to say, we'll set the learning constant to be small. And now we get into the interesting part. We're going to start running our for loop. And we can see this starts here. We have our for loop, and we're going to choose a variable k for our iterations, and we're going to go from k equals 1 to 2,000. So for 2,000 iterations, of our code, what we're going to do is first choose a random point in the xy plane. In order to do that, we're going to call this function rand_n, which returns a random value, and we're going to specify random x and y point. So this is some random point that lives in the xy plane. And then we're going to look at this point and compute our desired output. So what is the correct answer? In order to know that, we're going to call this function known answer, our step 1 procedure. Remember, to known answer, we specify the slope and intercept of our line, we specify the x and y coordinates of our point, and this function returns the desired output. Is it above the line 1 or below the line 0? We then move on to step 2. We compute our perceptrons output by using the feed forward function, where, remember, to feed forward, we give the x and y coordinates of the point, our weights wx, wy for these inputs, and also our weight wb for the bias term. This function returns the perceptron output, which is the perceptron's guess. Is that point xy above or below the line? So now we can move on to step 3. We want to compute the error. So the error is the difference between our desired output, is the point above or below the line, that's the correct answer, versus the perceptron's output, where the perceptron is answering whether or not the point is above or below the line. And then we're ready to adjust the weights according to the error. We're on to step 4. How do we adjust the weights? Well, we take our existing weight, let's say Wx, we add to it the error term, which is 0 or 1, times the input, in this case x, times the learning constant. And we do the same for y, where we take our existing weight for y, we add to it the error term, times the y coordinate of our point, times the learning constant, which we fixed above, remember to be 0.01. And finally, for the bias term, where you take our existing bias weight, we add to it the error times the bias value. Remember, we said above the bias is always 1. I didn't make a typo here, so in this case the bias, we've just set it equal to 1 times the learning constant. And here again we have this funny notation. We take our existing value for Wx, we update it by adding in this new term, and we take that new summed value and set it equal to Wx. So we're rewriting over the variable Wx as we update it. And the same for Wy and Wb. So this completes the repetition of our procedure, steps 1 through steps 4. And what we're going to show in the rest of this code is that each iteration of the loop, we're going to display the results. We don't have to do this, but it's nice to display the results to see how our perceptron is learning. And again, we've finished the analysis. So really, steps 1 through 4 are included in the highlighted region of code shown here. This is the full procedure to train our perceptron. The rest is just visualization. Okay, so let's look at these visualizations. Now the first thing is we want to compute the estimated slope and estimated intercept of our perceptron's guess. And to do that, we have to compute some seemingly confusing quantities. So we're going to set the estimated slope equal to this ratio of the weights. So we're going to take the x weight, the negative of that, and divide by the y weight. And we're going to compute the estimated intercept of our perceptron and set that equal to the weight of the bias term divided by the weight of the y coordinate, and again, a negative sign in front. Where do these estimates come from? Well, let's look at the equation that our perceptron is evaluating. So what is our perceptron doing? It's taking the weight Wx, multiplying by the x coordinate, plus the weight Wy, multiplying by the y coordinate, plus the weight Wb, multiplying by the bias. And if we set that equation equal to 0, that defines the boundary between an output of 1, where the perceptron guesses the point is above the line, or 0, where the perceptron guesses the point is below the line. So if we take this expression and let's solve for y, how do we do that? We move some terms over to the other side of the equation, so we move Wx times x to the other side of the equation. We move Wb times 1, the bias term, to the other side of the equation, and then divide by Wy. And we get this new expression where y is equal to this stuff. And if we look at this stuff, we see that the x term is multiplied by a negative Wx over Wy. This corresponds to the slope. And then we're adding to this another term, this minus Wb over Wy, which corresponds to the intercept. So these quantities determine the estimated slope and estimated intercept of our perceptron. Why is that useful? Well, it's useful to make this plot. And in order to make our plot, we're going to specify a range of x values. Let's go from -2 to 2 in steps of 0.1. And first we're going to plot the true line. This is the line where we're trying to get our perceptron to estimate, to find. Because if the perceptron can accurately estimate this line, then it'll do a good job of telling us whether or not a point is above or below the line. So to plot this line, we're going to take these x values from -2 to 2. We're going to multiply them by the slope and add the intercept, and we're going to plot it. So this will give us a plot of the true line. In this case, it'll be 2x plus 1. And then we're going to freeze our graphics, and we're going to plot our estimated slope times this range of x values plus the estimated intercept. And that'll give us the perceptron's guess of this line. And we'll hold off. So those are the two main quantities we're going to plot. We'll then label the axis or give a title to this plot, which tells us the iteration number that we're on. We'll start at iteration 1 and go up to iteration 2000 if we're patient enough. We label the axis x and y. This is our two-dimensional plane. And then we're going to specify a legend. The true line, this is the answer we're trying to get, will be in blue. And then the perceptron's estimate will be in red. So let's evaluate this code now and see how it behaves. So in order to evaluate this code, I'm going to copy everything from the beginning of this for loop to the end of this for loop and paste it here. So let's get oriented here. At the top of the screen is shown the iteration number, which is going to go from k equals 1 to 2000. On the vertical axis, we have the y coordinate, and on the horizontal axis, we have the x coordinate. The blue line is the true line we're trying to estimate. The red line is our perceptron's estimate. And what you might notice is initially, at a low number of iterations, our perceptron's estimate is not very good. Right? This red line is not a very good estimate of the blue line. That's because the initial weights we chose were not correct. As we give more and more data to our perceptron, we're now at iteration near 170. The perceptron's seen 180 and almost 200 points. And as the perceptron sees more and more points, it learns more and more, it adjusts its weights, and as it adjusts its weights, it makes this red line closer and closer to the blue line. So although the initial estimate for our perceptron where we randomly chose the weights was bad, as we let time evolve, as we give more and more information to our perceptron, training it with more and more points in the plane, it does a better and better job of estimating the blue line. And what you see here, we were only up to maybe 330 estimates, 330 points in this case. The perceptron's doing a really good job at estimating the blue line. And maybe this is somewhat incredible, right? We've taken this piece of code, our perceptron, and we've provided a procedure where it can learn. It can adjust its weights by given new information, given more and more points in the plane. It adjusts its weights until it does a better and better job of estimating this true line. The red line here, the perceptron estimate, gets closer and closer to the blue line. In the homework, you'll continue to explore the perceptron, feed-forward evaluation, as well as these learning procedures.